All right, good morning, everyone. Second day of CHES, welcome for that. So this is the first session of today. It's called SCA Microarchitecture. So we have three nice papers for you that deal with microarchitectural leakage. All right. Microarchitectural leakage has a bit of a dual use term at CHES. So it can either mean leakage arising from microarchitectural components like caches, right, branch predictors, so timing attacks. But then also kind of more recent line of work deals with how the microarchitecture kind of messes up your software masking and how you have leakage due to the microarchitecture in physical side channels. We have talks corresponding to both of these lines of work here in this session. So I'm really looking forward to that. Our first speaker is Yannick Zeichner, and he will present, I hope the slides will be coming up on the screen. All right. He will cook us up some pommes in the second line of work I mentioned, regarding software masking. Yannick, please take it away.
Yeah, thank you so much for the introduction and welcome to the presentation of POMMES, which is a joint work with my supervisor, Amir Moradi. Now, we are all aware that confidentiality, integrity, and authenticity of data in the 21st century is more important than ever before. And therefore, we need to apply strong cryptography to protect our data. However, while we have strong cryptography, it's often very difficult to apply it correctly such that it upholds the security level in practice. And this is due to the numerous attack vectors, and one of which are side channel attacks where an adversary can observe undesired side effects such as power or timing to draw conclusions about the process data. Luckily, with the masking countermeasure based on the principle of secret sharing, we have a strong defense against it. Here we split every secret variable into uniformly random distributed shares. And when we operate on those intermediates, we cannot draw any conclusions about the unshared value. Now, while both cryptography and side channel attacks can be applied both in hardware and software, in this talk, we'll focus on the software side here. And as we focus on the software side, it has been shown multiple times there is a discrepancy between theory and practice, namely that there is no trivial translation of masked software algorithms to the actual code, and this is due to multiple reasons. First of all, we have an increased abstraction level. For example, when we consider hardware masking, we have almost full control of the data flow and the layout. However, when we have software masking, the only way to interact with the hardware is by writing software. So the hardware remains unknown here. Next, we have the microarchitecture, which also remains proprietary. The microarchitecture defines how exactly operations and data handling are realized. Another abstraction level comes from the compiler. Now, even if you assume that your high level, for example, C code is secure, the compiler might introduce some translations or some optimizations, which can reduce the security on the final machine code. And lastly, many software algorithms are proven in a somewhat unrealistic leakage model, for example, the deep probing model. However, from hardware masking, we know that we require a more stronger adversary model, for example, the robust deep probing model, to encounter for physical defaults, for example, glitches and transitions. And the same actually also applies for software because the software is executed on the underlying hardware. Now at CHES 2023, we presented a leakage model, which is a black box model that incorporates multiple microarchitecture leakages found through research and practical measurements. And all those microarchitectural effects can be traced to glitches and transitions of the underlying hardware. Now, as this leakage model will be used for a security assessment later, let's have a short look at what the model looks like. First, we present here our generalized CPU layout, where we have a register file with capital R bits and a memory area M, and we can write values from the register to the memory and vice versa. Then we have an ALU, which performs all arithmetic operations, followed by an end-stage pipeline, and also hidden registers, which are not directly accessible by the software developer. Now, more precisely, those hidden registers are placed on a memory bus and between a register file and the ALU. So now that we know how the CPU looks like, we can derive the microarchitectural probes an adversary can place. And here we start with transitional probes, where an adversary gets the joint information of two successive values of storage elements. Now, what are storage elements? In our case, it's every register in a register file, every hidden register, and also every memory address in a memory area. Next up, we have vertical probes, and they occur during the register selection that will be forwarded to the ALU. Now, the register selection is realized by a large multiplexer. And if an adversary places a probe at the output of the multiplexer, glitches might occur, which can propagate back to each register in a register file. And therefore, the adversary gains the joint information of the eth bit of every register. Next up, we have horizontal probes, and they occur because of the always active nature of the ALU. Now, here, what this means is that the ALU performs multiple operations in parallel, and only the correct result will be forwarded to later stages. Now, the ALU does not only operate on bitwise operations, for example, XOR, but also has addition and subtraction, which combines multiple bits. And furthermore, the ALU does not only operate on one source register, but two source registers. So if an adversary places a probe at the output of the multiplexer here, glitches might occur that can propagate back to operations that combine multiple bits in pairwise registers, and therefore the adversary gains the joint information of all bits of pairwise registers. A second challenge I mentioned earlier are compilers. And while there are many different flavors of compilers, for example, GCC or Clang, what they all have in common, or what they all mainly do, is they translate high-level source code into a low-level machine code. And here you can see a simplified structure of a compiler where we have a front end, which is responsible for parsing the source file together with some syntactic and semantic checks, and translate the source code into an intermediate representation, which will be used in the backend. Now, the backend performs all the optimizations in machine-dependent and independent compiler passes. Now, in this work, we will focus on an important backend compiler path, which is the register allocator, and we place constraints on a register allocator such that the outputted assembly file is in line with our leakage model. Or more precisely, given a masked and annotated C code, we use the GCC front end together with the constraints we will introduce to our register allocation to generate ARM assembly, which is in line with our CPU-independent leakage model. Now, I already mentioned that the register allocator is an important backend compiler path, and this is because the intermediate representation of the compiler at this point only operated on virtual registers. And this is due to the fact that the compiler at this point, it eases the previous compiler passes that came before here. Now, the virtual registers usually exceed the number of physical registers that are available inside the CPU. So the goal or the task of the register allocator is now to map every virtual register to a physical register. And this is an optimization problem. Unfortunately, it's NP complete, but we have some good algorithms that can solve this problem reasonably well. And one of those algorithms is the linear scan register allocation algorithm. It is a greedy algorithm which runs in linear runtime and performs the register allocation on the function at once. For it to work, it requires a linearized intermediate representation, so no control flow graph, but just a sequential stream of instructions. Furthermore, every virtual register needs to produce or generate a life interval, and a life interval is a range that goes from the first definition of a virtual register to its last use point. And then the algorithm basically goes like this. We generate two lists, active and available. Now, available is a list that contains all physical registers that can be assigned to a life interval. And active is a list that contains a mapping from the life interval to its currently associated physical register. Now, we sort the intervals by increasing start point and start iterating over them. And then we try in each iteration to assign a physical register, an available physical register to an interval. Now, if no physical register is available, we need to split an interval, and this means we need to write the interval to memory, which frees its associated physical register, which can then be used for further allocation. Now, let's have a look at an example here, where we have 7 instructions with 4 virtual registers and their associated life intervals. And let's assume we only have 2 physical registers here. Now, we start with V1 and try to assign it an available register. In this case, this is R1, and R1 will now be removed from available. Then we go to V2, try to assign it also an available register. In this case, R2, remove R2 from available. Next, when we go to V3, we do not immediately try to assign an available register, but we notice that the interval of V1 fully comes after the interval of V3. So the interval of V1 can never interfere with any other register life interval that comes after. So we can remove the mapping from active that is associated to V1, which basically frees the register R1, which is now available again. And now we can assign an available register to V3. Now, in the last case, we cannot remove any mapping from active, but there is also no available register here. So we need to spill an interval. And while there are many heuristics, we chose a heuristic to spill an interval with the latest endpoint, which is in this case V2. So the interval of V2 will be moved to memory, and its associated physical register R2 is now free for assignment. So the virtual register V4 gets assigned the physical register R2. And with this, we have our final mapping between virtual registers and physical registers. So now that we know the adversary model and how the register allocator works, let's have a high-level overview of POMIS. Now, given a masked and annotated C code, we use the GCC front end to generate the intermediate representation. Then we parse it in our own data structure, and we perform information flow analysis to evaluate which virtual registers and which instructions handle sensitive data, perform our constrained register allocator, do some security-related post-processing, and finally output the assembly. Now we start with POMIS by the information flow tracking, and therefore the user needs to annotate which inputs to a function are secret, which means that it contains share-related information, or public, which means it does not contain any share-related information. For the actual information flow tracking, we use Kildart's worklist algorithm, which operates on a control flow graph, and each basic block in a control flow graph will get two lists, one for the sensitivity of incoming virtual registers and one for the sensitivity of outgoing virtual registers. Furthermore, we need a work list which contains all basic blocks that we need to visit. And then we iteratively remove a basic block from the work list, perform our information flow analysis sequentially on each instruction individually. And if the sensitivity of a virtual register in this basic block changes, we add its successors to the work list. Now, I already mentioned that we have to perform the information flow analysis on each instruction individually, and therefore we need to define a function which tells us exactly that, so how the information flows within one instruction. And here we distinguish between three cases. First, we have arithmetic instructions, where we say when at least one source is secret annotated, the destination will become secret. When we load from a secret annotated memory address, then the destination will become secret. And when we store a secret annotated value to memory, then its associated memory address will become secret. So now we need to make sure that the register allocator is aware of the adversary model and also which constellations are harmful. And therefore, we say that to tackle transitions, we do not allow a secret annotated register to be directly overwritten by a secret annotated live interval. The same also holds for hidden registers, where we do not allow two subsequent secret annotated loads and no two subsequent secret annotated stores. And furthermore, we have to take into account the memory area and each memory address, so we do not allow a secret write to directly to a secret annotated memory address. Now, if two intervals, secret annotated intervals, are in the register file at the same time, a vertical probe is able to access both secrets at the same time. So to avoid this, we only allow one secret annotated value in each register file at the same time. And what this means is that sensitive annotated live intervals must not overlap. And how do we achieve this is by dividing each secret annotated interval into the minimal number of disjoint ranges. So for example, here consider V1 and V2, both are secret annotated. And here on the right-hand side, you can see what the intervals look like when we divide them into the minimal number of disjoint ranges. While yes, this creates gaps, and during these gaps, the value of V1 needs to be moved to memory and then reloaded afterwards. Now, we also add sensitivity information to the available and active list. So in the available list, we add the sensitivity of the previously assigned interval. And in the active list, we add the sensitivity of the currently assigned interval. Now, to select which registers are available and non-harmful to assign to a live interval, we distinguish between two cases here. First, if our current live mapping has a public annotation, we prioritize secret annotated registers in available, because this would create a transition between a secret and a public value, which would create a non-harmful transition. Now, if our current live mapping has a secret annotation, we first check if there is a previous sensitive interval that is tangent to our current interval. Now, if two sensitive annotated intervals are tangent, this means that they share the same instruction. And under the assumption that the mask C code is correctly masked, this does not create a harmful transition here. Otherwise, we prioritize secret annotated registers from available, while yes, this would create a harmful transition between two secret annotated values if we would not assign it to a secret annotated register, but other public annotated register, we would create a vertical leakage, which is much harder to mitigate afterwards. Now, in case of spilling, we also have some restrictions here by saying that we never spill a secret annotated interval, because spilling a secret annotated interval would further create secret annotated loads and stores, which need to be handled and which creates much more overhead. Furthermore, from a security standpoint, every secret annotated live interval is already optimally divided in terms of vertical probes. Now, after register allocation, we need to perform some post-processing, because let's remind us that the linear scan register allocator requires a linearized intermediate representation. So at this point, we do not have any control flow information here. And therefore, we need to check for violations that only occur under nonlinear control flow paths. So for example, here, consider on the left-hand side, the live intervals where the orange intervals are secret annotated and the blue ones are public annotated. And on the left-hand side, we would not see any violation in terms of transition or vertical violation. However, when we consider the right-hand side of the control flow graph, the control flow graph on the right-hand side, and assume that the register of V5 and V1 are different, and we take the branch or the path from instruction 2 to instruction 7, we would in fact get a vertical violation between V1 and V5. Now for our evaluation, we conducted a two-stage evaluation. First, a simulation-based approach with ProLead SW, which performs the verification under the CPU independent leakage model I talked about earlier. Here we performed 10,000 simulation with microarchitectural effects enabled. And also afterwards, we performed practical measurements where we collected 100,000 traces for each case study with a picoscope oscilloscope and a sample rate set to 250 megasamples per second. Now, all power traces were collected from an STM32 microcontroller with a Cortex M0 Plus processor. And for the evaluation of the fixed versus random t-test, we used SCA lib. Now, to look at the case studies, we created with POMIS 8 functions in total, which is a refresh gadget, an SW AND gadget, a Piney multiplication gadget, and a full AES box, which is constructed by 5 functions, so in total 8 functions here. Why do we choose exactly those 8 functions? Because we showed that we can create secure code, which is, we can create functions that have non-linear and linear functions with different security notions. And we can also handle nested functions, as is in the case for the AES box, for example. All 8 functions were created in a first and second order fashion, and we could not detect any leakage in any of our test cases here. While our case studies are secure, it comes with a drawback in terms of efficiency. For example, here, if we compare the POMIS-generated code with the GCC unoptimized code, we see that we have an overhead factor between 1.3 and 3.5 in terms of clock cycles. Now, the reason for this are multiple. First of all, we have a already very over-conservative leakage model. And together with the conservativeness of constraints, we explain the overhead by this. And furthermore, we have a complexity discrepancy between POMIS and GCC. GCC is a long-living compiler, which is a full integrated compiler with every phase, while POMIS solely focuses on the register allocator here. However, we argue that the primary goal of masked software is its security. So it doesn't matter how fast your masked software code runs. If it's not secure, then it does not fulfill the purpose of software masking or masked software in general. Now, to conclude what we did here in our work, we introduced a side-channel secure register allocation algorithm under the CPU independent leakage model. We can handle masked C code with arbitrary control flow, loops, and internal function calls. Internally, what POMIS does is it performs static information flow analysis. We have placed constraints to the linear scan register allocation algorithm to be in line with our leakage model. And we emphasize the necessity to perform post-processing logic for nonlinear control flows. Afterwards, we evaluated the security of multiple masked software implementations that we generated with POMIS, and they range from single gadgets to a full AES box. In total, we generated 8 functions, and for all 8 functions, we generated first and second order designs. And with this, I end my talk, and thank you for your attention.
All right, thanks a lot, Yannick. If there's any questions, please move on over to the microphone. Please go ahead.
Yeah, thanks for the talk. Let me say that when you checked the leakage after applying POMIS to the code, there was no leakage detectable. Did you also check if this gadget would have leaked just using GCC?
Yes, we actually did. We did for different compile optimizations, so 01, 00, 02, or 3, and we measured all of them, and everything leaked in 00 optimization, except the Piney multiplication. But let me stress this, that this is just basically a gambling. I mean, for example, if your register allocator combines 2 shares or writes one share in one register and overwrites it with another share, then you create transitional leakage, which leaks pretty fast. So we could have maybe wrote the code in any different way, where the register allocator would now assign registers to different values, and then maybe we would have seen leakage. So that's a point to that.
Yeah, thanks.
Hello, great talk. Can you get back to the microarchitectural view?
You mean this one?
No, the sketch of your microarchitectural model. Because I was wondering, using register allocation, how can you prevent a transition leakage in the memory register? In the
hidden register?
In the register, can you get back? It was in the first slides.
Just say stop. No.
It was when you introduced your model of microarchitecture. Yeah, in the shadow register, how, using only register allocation, can you prevent transition leakage in the shadow register between with the memory?
Yeah, good point. This is basically also part of the post-processing, where we remember where we have a load or store operation, and also track the sensitivity inside in this hidden registers. So for example, we have the sensitivity in register R0, then we perform a load, and during this load, we will write it to memory, and while we write it to memory, it will also be placed in the hidden shadow register. So we remember when we load a value, which sensitivity it has. And during the post-processing, we also check if there are sequences of load, not directly successive afterwards, but can be 10 instructions apart, what sensitivity they have, and if they have a harmful transition, for example, 2 secret annotated values, we basically perform a dummy override to a non-critical memory address. For example, storing the stack pointer to a dedicated place in memory, which would then clean the hidden registers, and you only have then a public value, and then there's no transition.
All right, we have time for one more question if there's interest in that. Otherwise, let's thank the speaker for this great talk. Well done. All right, the second talk of the session is entitled Evict, Inspect, and Time, Exploiting Out-of-Order Execution to Improve Cache Timing Attacks. This talk will be given by Chichenok. So please, we're all ears.
Well, thank you very much for the introduction and good morning, everyone. And as the chair has already introduced the title of this talk, so it will be about cache timing attacks. And since I assume this is the first talk about cache timing attacks, so let me introduce or recap what cache timing attacks are. So in cache timing attacks, so we basically exploit differences in the timing execution, and in particular when we access data, whether it is in the cache or not in the cache, and that can see the differences. So if we take a look at this illustration, so if we check and the data is in the cache, then we can get the data or the cache, can get the data quickly, and that is called cache hit. And on the other hand, if the data is not already in the cache or cache miss, then we first need to get the data from the memory and then put it in the cache for potential future usage before we can use it. So it is slow. And with these differences in the timing, cache hit and miss, and fast and slow, there's a distinguishable latency. And what do I mean by that? I assume that you agree with what I say so far, but let's take a look at some experiment. So if we look at this graph where the x-axis is the execution time and the y-axis is basically how many samples when we perform the experiment. And blue is cache miss and orange is cache hit. And it is not a surprise that what you see here is that for cache miss, we have a longer latency. It's not a surprise, but there's a little bit of challenging problems. Well, because this one, what we did, we actually measure a single memory access. But why do I say it's a little bit of issue? Because in some cases or in some attacks, we don't really measure a single instruction when we measure the latency. We actually measure longer than that. And one example is evict time attack, previous work evict time. So let me recap how this evict time works. So with the evict time attack, there are basically two main steps. So the first one is the first step is evict. What it does is that it removes victims' data from the cache. So let's take a look at this illustration. So assuming that victim has already run the execution and there's some victim data in the cache, and what I'm considering here is set associate cache, where the cache is divided into multiple cache sets. And in general, a memory line can map to the same cache set. And by doing so, we can evict the data, the victim data that's already in the cache. So that's the first step. So once the data is removed from the cache, then we let the victim execute and then we measure the time. And with this, when we measure, we can see here that we don't really measure just one single instruction, but we measure multiple instructions. And then when we come back to the previous question, well, if we measure multiple instructions, but what we have seen in previous graph, or what we think about the latency of the cache access is only a single memory access, then why does this work? And this attack works because if there's any miss in the entire execution, we see that the overall execution time would be longer. So we say there is a cache miss. And with this, we say that the latency is additive. But is it really the case that the latency is additive? With that, so we do some more experiment. And with that, I actually want to bring back the result of the previous experiment and how we did it. So to get that graph that I showed previously, we ran this piece of code with actually only these two lines. The first one is just linked list, and the other one is another memory access. And this is the graph that you have seen before, which not a surprise that we've seen this. But with this same piece of code, just these 2 lines of code, we can actually get this result as well. And with the result on the right-hand side, we can see that the latency or the execution time of cache hit and miss is nearly indistinguishable. And then what's going on here? So the differences is that on the first graph on the left-hand side of the previous one that I've shown, so this one, the first line, the linked list is cached. So with the linked list is cached, so we can execute the first line very quickly. And then the second line is actually what we, when we say cache hit or miss is actually the second line. So if it's hit, then it's quick. If it's slow, if it's miss, then it's slow. But on the right-hand side is the case where the linked list or the first line is not in the cache. So when it is not in the cache, then we have cache miss already in the first line. And then for the second line, if it is a hit, then again, the first line is already slow. When we measure the overall execution time, it's slow. But if both lines are, well, if both miss, so the first line is slow, but second line is also slow. But then if we can perform these 2 in parallel, then the overlap in cache miss, well, there's a overlap in cache miss, and then the overall is, we can just see as a single cache miss. So to quickly summarize this one, so we say that the latency is not always the case, that it is additive. We can perform parallel execution. Now, let me summarize the observation that we have seen so far. So we see that in parallel execution, the latency is not always additive. And with out of order execution, where we can reorder the instruction, then with the out of order execution, then the program doesn't always execute in the order, so we can rearrange it. And the latency of cache miss is not always slower than the cache hit if we have these 2 conditions. So the first one, if there are enough instructions to bring forward in the case of out of order execution. And then the second one is that if the total latency of those instructions is at least cache miss, so that we can hide the cache miss latency. So now this leads to the question of how exactly the latency and out of order execution, how the interaction between them. So we need to understand more about this thing. So we perform some more experiment. So the next one that we do, we want to understand how the latency can be hidden. Experiments that we did are quite similar to the first one that I have shown. But this time, so previously we had like first line linked list and the second line memory, another memory access. So this time we add other instructions in between. And in the first case, we add knob instructions, like the number of knobs depends on the experiment. And we use knob because it nearly consumes any computational resources, but it occupies lots when we need to reorder instruction. So with this experiment, this is what we got. So at the beginning, we can see that the latency of cache miss and hit are nearly the same, but at some point, we see start increase in cache miss. And that is where we are running out of resources. Imagine if we need to reorder the instruction and we put a lot of knobs already, and we cannot, well, we still need to understand like when we reorder in which order in the end that we get the final result. So we need to remember the order as well. So that was the first experiment. And you might wonder whether we can use different instructions other than knob. Yes, so we did a different experiment, quite the same structure, but instead of knob, we use compare instruction. So with this case, we see similar trend for the result. So at the beginning, the latency of cache hit and miss are quite the same, but at some point we see a sharp increase in the latency. I forgot to mention that the x-axis is the number of instruction, and then y-axis is the time. execution time. So the same thing that at some point we are running out of resources, in this case, reservation session, if we need to keep tracks of dependency. So with this, let me summarize again our findings so far. So we see that with out of order execution, we can rearrange instruction, but then its capability is limited on the resources that we have. And this is to re-emphasize again what I've already shown. So the cache miss is not always slower than cache hit. It depends on whether there's enough instruction that we can bring forward and whether the total latency of those instructions is at least of the cache miss. And what we have seen from previous slides is that for the latency of cache miss itself is not constant. It depends on how much we can hide or the overlap between the execution time. And with all of these, it leads to if we can control resources and if we can manipulate the overlap of the execution time, then what we can do is that we can identify when the cache miss occur. And previously with cache timing attack, we usually detect whether the cache miss happened, but this time we can say when in addition to whether it happens or not. And this we introduce and improve attacks, which we call evict time, which we can get more information instead of whether we get when the cache miss occurred. And before I show the attack on AES, I would like to briefly recall about AES, particularly on decryption. Well, before that, I would like to give an overview of spec evict time first. So with evict spec time, so we have two steps as well. The first step is to evict the memory from the cache. This is the same as in the evict time attack. So if we have victim memory in the cache, so we run spy and then we evict some data. And then the next step is that we do spec time. So we let the victim execute again, and then we measure execution time. Same as previously, if it is slow, then we say that there's a cache miss. But if it is fast, there are two situations. The first one is that there's no cache miss, or there is a miss, but it is in an early stage. If the miss occur early on, then we can bring enough instruction and then we can hide the latency of that miss. Now, so let me really introduce the AES decryption. So because it's decryption, so we start with ciphertext and then we go to plaintext. So just briefly recap for AES decryption. So we have several steps. So add round keys and then inverse ship row, inverse sub byte, mixed column, and add round key. And this iterate for 9 rounds if you consider 10 round AES. And then the last step is another set of inverse ship row, sub byte, and add round key. What I want to focus on is towards the beginning. So with the first step, so what we have here is that we have ciphertext XOR with the key, and that is used as an index to a lookup table. And with the lookup table, so this is where the memory access occurs. And to do a little bit of calculation, if we assume a cache with 64 sets, and there are two main types of AES implementation. The first one is T-table. And with this case, we have for the table, we have a 256 entry of 4 bytes each. And if we do a little bit of calculation, and that is 64 cache lines, and that translates into 4 bits. So if we can get the information of access here, what we can recover is 4 bits of information. And another type of implementation is SBox. And in this case, we have 256 entry of 1 byte each. And if we do some calculation, so this translates into 2 cache lines or 2 bits. So if we can get the access, then we gain 2 bits of information. Okay, with this background on AES, so let's take a look at how we attack T-table implementation. So first, I will give the concept of how we do this. So we target the first round, and as I previously mentioned, that index XOR key bytes, if we know this, then we get the key. And from previous calculation, we can gain 4 bits of information. So 4 out of 8. So we can recover half of the key. And for ES, we only perform, for T-table, we only perform this proof of concept. But for the next attack, we recover the full key. So what we do here with expect time. So we evict, we have like target cache line that we want to monitor, and we evict that part. And we can doing so by like a previous eviction, and then we do some manipulation of how we control the timing overlap. And we can do that by, for example, exhausting the reservation station or reordering buffer. And then with that, when we manipulate, we can like set how many instructions that we fit in the buffer. And then we do that in the way that we only allow the first round of instructions, the first round of AES to enter those buffer. And in this case, if we see that we can detect whether the cache miss is occurring in the first round or in later round, because all in the buffer, we only have instruction for the first round. If it is fast, we say that there's no cache miss, or it's happened in the first round, or if it's slow, then there's miss in later round. And with that, to give, and then later on we guess and we use Pearson correlation. And to compare the result, we compare our result with the previous evict time attack in terms of when the access happened. So with previous work, they consider the anti-encryption or decryption. So the miss can occur in any round. But then with our expect time, we can focus more with those manipulations. So if we only fit the first round, then we can detect whether there's access in the first round or later round. And if we consider, if we calculate the probability of not accessing, so this is where we get the information of access. So roughly with if we expect time, the probability is small, not negligible, but it's quite small. It's only 8%. But with if we expect time, we have more than 70%. Because we can target a particular round, not just any in the 10 rounds. And in terms of the number of samples, because we have higher probability, then if we compare to evict time requires 2,500 roughly to guess the correct key. But for if we expect time, we only require roughly 250. And again, this is not a surprise because we have roughly 10 times more, like higher probability, then we have roughly 10 times smaller number of samples. So that was the first attacks on T-table. And for the S-box, I will not have much time to go into detail. I will just give an outline of the attack. So the attack consists of 2 steps. So the first part, fairly simple and straightforward. We detect the access and we can get 2 bits of information, just like we've already seen. And for the second step is where we get the remaining 6 bits by doing some manipulation on how much instructions that we allow them into the buffer or into the resource that we have. Particularly, we manipulate whether we get only the first round instructions or first and second round. And we use this structure of codes. So we have 2 access instructions. And these 2 are separated by some other instructions that we can manipulate, how many of them. And then the last one is the AES decryption. And then the way we do it is we just manipulate how many, in this case, NOP instructions, and whether we just want to have only the first round instruction inside the buffer, or we allow the first 2 rounds of instructions, and that we can detect whether the miss occur in the first round or the first 2 rounds or the later round. And just to summarize, what we've seen here is that the latency of cache hit and miss can be the same. And even for the latency of cache miss itself is not constant. And with this, we introduce EV-expect time, which we can identify whether and also when the cache miss occur. And for more information, I would like to encourage you to look at our paper. And that's all that I have. Thank you very much.
Thank you for the talk. If you're interested in asking a question, please move on up to the microphone. In the meanwhile, I was wondering, could you talk a bit about, so this is a nice improvement to evict and time. Could you talk a bit about, can you use this can an attacker use this anytime they could also use evict and time, or are there more constraints to getting this increased resolution?
So I would say the main thing is that you need to have the way to manipulate the resources. So like if you can insert the code, so that's one way, but that could be kind of like artificial. Otherwise, if you have this kind of structure, then you can manipulate how many instructions. And for AES code itself, we see that they already have that kind of gadget by itself. So we didn't really need to have any more thing to do.
All right. Okay. In that case, let's thank the speaker again for this great talk. Then let's move on over to the third and final talk of the session, which is entitled TEE Jam. I'm looking for the speaker in this room. Oh, there you are. Fantastic. So our speaker is Florian Siek, who will be talking about an attack that you thought was gone, but it strikes back. And let's hear all about it. Take it away, please.
Hi. So yeah, I'm Florian Siek, and today I'm presenting TEE-Jam, sub-cache line leakages strike back. And this is joint work with Zion, Sebastian, Chichanok, who just presented here, and Thomas and Yuval. Yes, so. Okay, so let's have a look a bit of like what kind of attacks we actually have in the wild in terms of attack resolution and in terms of attacker models. So today there is like this big trend to move your computations into the cloud or into a different, someone else's computer. So you basically prepare your code and you put it there. But what does that actually mean? Also, all your sensitive computations are there, all your sensitive data, and well, other people do the same. But do you know whether you can actually trust all those other people? Well, probably not. They might just decide to attack your code and steal some of your data. And yeah, since there's maybe not perfect isolation, they might even succeed. So people thought, what can we do about it? Yeah, and they came up with the idea of trusted execution environments, as for example, Intel SGX or AMD SCV. And these are supposed to isolate your execution and protect your sensitive data. And also what is, of course, then necessary is that those solutions offer some kind of attestation mechanism so you can be sure your software really is running in such a trusted execution environment. However, what this also does, it introduces some kind of new attacker model in which the attacker suddenly has access to the kernel, to the BIOS, and they can basically modify the whole system and thereby probably gain better resolution. So what we ask is whether cryptographic implementations today are sufficiently protected against these attackers and whether we can actually even break side channel countermeasures with these privileges. So let's have a short look at previous work. In the recent years, there has been a plethora of attacks on trusted execution environments or code basically running in cloud environments. And well, yeah, first of all, there are single stepping attacks, which have been enabled by SGX step or SEV step, which was just presented in another session today. And yeah, one example of these attacks was, for example, Nemesis, which is measuring the single stepping time of every single step. And since different instructions take different amount of execution time, they could infer the control flow and thereby gain access to secret data. Then there are other attacks which use speculative effects or out of order effects. And yeah, another recent example was also utilookup, which combined a prime and probe attack with single stepping and was able to use a minute leakage in an RSA key decoding implementation to leak small RSA keys. More recent works are, for example, ciphertext side channels as well. So let's have a bit more, let's have a look at like primitives that we can use to build a new primitive that has a very high spatial and a very high temporal resolution. So I just mentioned the single stepping, which gives us a very high temporal resolution, and that one of these frameworks for SGX step is, or one of these frameworks is for SGX step, and it's called SGX step. And it basically works by having the attacker being like, or the attacker being the host app, yes, and starting the victim in an enclave. And then the attacker is also in control of the APIC timer, which is like a rather rough timer, so you cannot interrupt the CPU per instruction, but well, maybe like 60, 70 cycles or something. And then the attacker will program this timer to interrupt the enclave. This will then execute some attacker-controlled interrupt handler, and from there we can execute some custom attacker logic, reprogram the APIC timer, and resume the enclave. So, but how can we actually interrupt always after the first instruction? As I just said, this APIC timer is rather, yeah, it's not that precise, and that's achieved by some by a microcode-assisted page walk, which is caused by SGX step to ensure that the first instruction actually requires more time to execute. So now we have like a means for executing or inspecting a program in the trusted execution environment step by step. But now we also want to have a higher sub-cache line resolution. And there was in the past, there was cache bleed, which achieved this using cache bank conflicts, but this is actually fixed today. Another attack that is, that some of you might still know is memjam, and that uses read after write conflicts caused by 4K aliasing. But in this attack, the attacker always observes like the full execution of the program, meaning of like an encryption of something with AES. So this is not really precise in terms of temporal resolution. So what we like to do is combine these two things and thereby achieve both a high temporal and a high spatial resolution. So before I introduce our new attack primitive, let's have a short look at how memjam or the read after write conflicts with 4K aliasing actually work. Let's assume we have some thread or two threads which are running on the same physical core. And the one thread is writing something to memory to a specific offset within the page, here 660. And yeah, this write is ongoing. Then another thread will be reading from the same offset, but a different virtual address. Since the processor cannot know whether these virtual addresses actually point to the same physical address, there has to be this has to be resolved first, and this will introduce a delay to the read. This is why this is called then read after write conflict. And why am I depicting 4 boxes here? Yeah, that's because even if I address 1 byte, the conflict will always be on a 4-byte level. So this introduces a little delay, and that delay is measurable. Now let's conclude on how we can combine these two with in our attack primitive tjam. And yes, we will use tjam to actually show that we can use very, very small leakages in cryptographic implementations, for example, RSA key decoding, to even reconstruct customly or commonly used keys like 4096-bit. And we will also show that we can break cache attack protected implementations of AES. In a brief overview on how TGEM works is we basically have an attacker thread that will constantly write to some specific offset in a page that we want to probe and cause a delay with. And then on another thread, the attacker will start an enclave and basically do, I think the battery is getting low, and will basically, do the SGX single stepping setup as I explained before. And in the custom attacker logic, the attacker will measure the single stepping time and thereby be able to differentiate whether there was a delay or not, and then record the single stepping time and do this for every step of the program execution, and thereby obtaining a full trace. The 4K aliasing, however, is statistical in nature because the conflict might not always occur because of the ordering of the instructions, or the amplitude might slightly differ. So what we have to do is we repeat this trace collection several times, then superimpose the traces and basically build the average per step. So we did evaluate this primitive by building a toy enclave, which always accesses an offset that is not conflicting with what the attacker thread is doing, and one which is conflicting. And then we average over, well, basically all the instructions in that are conflicting and non-conflicting. And what we obtain is this nice histogram, which shows the number of cycles for both cases. And we see that for the conflicting case, we actually have a delay of about 130 cycles on the machine that we have been using. And then we've been observing several of these conflicting, non-conflicting events. And then we basically, when we average over those, we can differentiate them. So how can we use this to attack crypto primitives? And as I said before, we are having two case studies, one on RSA and one on AES. And the one on AES is actually a T-table implementation from Wolf SSL, which is protected against cache line level attackers. And so before I explain on how the attack actually works, I will shortly explain on how the cache line level protection works. And that basically just works by, this basically just works by accessing every cache line in a T-table. So if I access one element in the T-table, I just access every cache line in the T-table, always with the same offset. Is there some other means to forward the slides? I can try to make do, but it's okay. So they will always access every cache line, and then select in constant time the correct entry of the T-table. So a cache line level attacker, they will just not see what was happening because every cache line was accessed, and the constant time selection, they cannot expect that. So with TGEM, however, we can just attack one offset within the T-table, and then if the victim then accesses every cache line again, we will have a conflict in one cache line and measure this higher delay. So, however, we would be doing this for every cache line, right? So if another cache line and an element in another cache line would be accessed, then we also would have that. So we cannot actually have just this red dot as our resolution, but we basically have this vertical line here, which is 64 bytes again. So we have the same resolution as a cache attacker would have. Then finally, what we do is we recover the last round key bytes by using a known ciphertext attack and the difference of means-based distinguisher, meaning we basically just make a key guess, and then we make a key guess, and then we divide our measurements into two sets. And if the key guess for the last round key byte was correct, we will see that that one set actually has a slightly higher single stepping time and average than the other set, which is here about 50 cycles, and well, it diverges from 0, as all the wrong key guesses, they do not. And yeah, we compared our results with MemGem, and if MemGem basically analyzes the full execution in the enclave with the 4K 4K aliasing conflict, then they require about 3 orders of magnitude more samples to actually recover half of the last round key bytes. Okay, so and finally, let's also have a look at an attack case study on RSA, where we attacked the same example as util-lookup did when they recovered small keys from the RSA key decoding process. So RSA keys have to be loaded into memory before you can sign something or decrypt something. And usually RSA keys are stored in PEM file format, which is basically base 64 encoded ASN1. And yeah, this file will then contain a lot of parameters with a lot of redundancy to apply the Chinese reminder theorem. And yeah, so what we will do is we will attack exactly this translation process from the base 64 decoding to the binary decoding. This is done in OpenSSL with a lookup table. And this lookup table basically fits into 2 cache lines. And I'm now showing, first of all, what util-lookup was doing with the cache attack and what the problems or the remaining issues have been with that implementation. So if this lookup table fits into 2 cache lines, what you the information you can basically gain is about 1 bit per access. These symbols are not evenly distributed, so you even get less than 1 bit per lookup. And however, the authors succeeded in, or we succeeded in capturing this with a single trace attack. And then we also observed there was some speculative effect, meaning usually just tracing or just collecting this with a single trace will result in not being able to observe the correct cache accesses because of some in the out of order execution. Also, as we just heard, probably both of those cache sets will be accessed every time. But there was a countermeasure for LVI, and that introduced pans into the enclave code. And this allowed us to basically distinguish these cache accesses. However, it was still only sufficient for small RSA keys with reasonable computation and time efforts. I mean, if you invest like billions of dollars, maybe you can also reconstruct larger keys, but with reasonable effort, this was what was possible with the attack. So we thought we also want to reconstruct normal or like commonly used keys, about 4096-bit even maybe. So with TGEM, we can actually subdivide this lookup table into more partitions than we can with a cache attack. We decided for partitions of 8 bytes of a size of 8 bytes, and this actually gives us the leakage of 3.3 bytes per lookup, a bit per lookup, sorry. And this is more than half of the information that is contained in each symbol. So that's really a lot. Okay. So in short, how does this attack work? We again have the attacker, which will single step the enclave, which is running the base 64 decoding. And on another thread, we have the attacker writing to some specific offset in this, which corresponds to some specific partition of the lookup table, and thereby probing this specific partition. And the attacker, they will constantly write to this specific offset and then single step the enclave. And after every step, they will record the single stepping time, collect the whole trace, and repeat this process, superimpose the traces, as I explained before, and build the average. So let's say we are currently probing partition 7. So the attacker will be writing to some offset exploiting the 4K aliasing read after write conflict, which corresponds to this partition 7. If there is an access to this partition, we will observe the higher delay and we will know, okay, this partition was accessed, so it's either A, B, C, D, E, F, or G. That is what we then learned for, I mean, this is why I said it's 3.3 bit, not 6-bit here. But yeah, we learned a lot already about the key. And yeah, this box plot here, it shows an example of attacking one of the lines of the PEM file. Both plots show the attack on a different partition. And every time we have a box which has a higher delay here in dark blue, it actually shows us that we think there was that partition was basically accessed due to the delay we measured of the single stepping time. And then we compared it against the ground truth. And yes, we saw that this was actually working. So we could see by the delay that that what the victim actually was decoding, and so we could recover key information. To build an end-to-end attack, we still needed to implement some alignment because base64 is just 6-bit per symbol, but we had to translate that like 4 symbols into 3 bytes, and then you have to align all those offsets. And we had some missing information because of, well, noise. And then we also had to make sure that the key reconstruction can handle that. And then we were using the key reconstruction from uToLookup, which is based on the one from Hininger Shacham. And yeah, during our experiments, we realized that the newest RSA specification actually defines Carmichael totient instead of Euler totient. And these Carmichael totient, they are a bit smaller for higher performance, but the key reconstruction just doesn't work with those. So we also extended the key reconstruction for handling these totient. And there's a lot of details on this in the paper. What is the important takeaway is that this required more initial candidates which had to be brute force, but due to the high amount of information we get from side channel, this was not an issue. So we were still able to recover even 4,096 bit keys in 18 seconds to 1 hour, depending on the size of the totient and on a 128 logical core machine. So in conclusion, and I think I have to wrap up. In conclusion, yeah, we presented a tech called TGEM with a very high spatial and temporal resolution. We can basically break cache attack level protected implementations or resistant implementations. And this actually shows us that it's very important that cryptographic routines are implemented in constant time without compromise, and that this is not always yet given. Also, as a contribution, we extended the key reconstruction to handle Carmichael totient. And we published the attack code and the key recovery code on GitHub. Thank you for your attention.
All right, questions for Florian? From my side, I just want to thank you for this finding. Because there was this folklore belief, as you mentioned, that okay, if the leakage is finer granularity than cache line level, everything should be fine, right? And it's great that you provide counterexamples to that, and maybe in the future we will never see this again. Let's hope for that. I also have a question, because you mentioned in the other session there was SEV step, right? Which I believe is also from your group. Would it be possible, because I guess AMD CPUs also have memory aliasing, and they also have a single stepping framework now. Would it be possible to mount these attacks on AMD CPUs as well? Could you talk a bit about that?
We tried to find the 4K aliasing on AMD CPUs as well, but we couldn't measure a delay there. So we were only able to measure it on Intel CPUs. That, of course, doesn't mean it's not there. However, during our experiments, we could only measure it on Intel CPUs.
Okay, thank you. More questions? If not, then let's thank Florian one more time. And with that, that's the end of the SCA microarchitecture session. Thank you so much for joining us, and enjoy the coffee break.